Hey YouTube, this is diveflyfish. Just want to show you the next design that I'm going to make with regard to the polycrystalline cells. Now, with the taffy-like material that we utilize that has some resiliency to it, we're able to apply a pressure to it, but it's very difficult to pull the things apart. So what I've decided to do is to make a pile cell with the magnesium and the graphite blocks, but as a means of placing it in a clamp and having it rebound. I think the simplest way is to build in an internalized elastic rebound system, and that could be something as simple as a couple of O-rings that will be placed on the magnesium after the polycrystalline material is placed here. Then we can sandwich the carbon on top of that such that when we have it in a clamp, we provide a clamping force. The clamping force will be buoyed up with the polycrystalline resiliency, as well as the elastic O-ring will prevent these from becoming bottomed out, and with the release of the pressure it will provide a counterforce to move the two plates apart, or so is my theory. So in any event, just want to give you an update as far as how I'm making that before I put the polycrystalline material in there, and that way we can also stack a bunch of these together and stress them concurrently or separately, either way, and build a system such that we have the ability to bolster the voltage and current not only by increasing the number of cells, but by also increasing the overall level of displacement. So for what it's worth, I'm going to give her a go, and we'll go from there. Obviously I don't have that stacked perfectly, but with the polycrystalline material it should be interesting to see what we can do from a compression standpoint. So for what it's worth, next step, build the cell. Hey YouTube, these are the cells that I made. These little 3-inch carbon ones. Put two of them together like so, and you'll see it's definitely produces enough voltage and current to light this. So this is one of the little white LEDs, and that's without an oscillator at all. So hang on one second, let me see if I can get this thing lined up here. So if nothing else, see, it's definitely gives enough juice to do that very brightly. So there's enough current to run bright LED off these two cells. So in any event, have some more work to do with these, and we'll go from there. Again, I don't think one will do it, so we can double check that, but two of the cells for sure will light the LED, but one no, two yes. No problem. So, for what it's worth. Hi guys, this is diveflyfish. Just want to show you something. This is the current reading. I have two cells in this pressure container. Two of those 1-inch by 3-inch carbon magnesium cells with the polycrystalline taffy-like cell. That's the milliamp hours reading right now, okay? And I'm at ambient pressure, so I've opened up the valve. I'm going to shut the valve now, okay? And we're going to do a pressure test, and I want you to watch the milliamp hour reading, okay? So we are at roughly about 50 psi, just shy of that, and there we are. So I'm going to take her up a little bit more. It's about 65 psi, okay? And I'm just going to put this down, and I'm going to pump it up just a little bit more, see if I can get this to stay there. Actually, I'll just try to hold it. It's hard to Use the bicycle pump with one hand, but I'll give it a go. So it's the change, perhaps, the rate change in pressure that imparts the piezo effect. But it sort of bounces up and down. It's a very interesting phenomenon. You see, go up and then down and up and down and up and down. So there's obviously a stress being applied to that polycrystalline material that's causing a change in current. Give her a go a little bit higher. So now we're about 85 psi. Okay. Goes down. I'm going to pump it up, see if I can take it to 90 and see what it does. Okay, it's 90. Up and down. Okay, so we have 90 psi on the bicycle pump. And the milliamp hours is seemingly to decrease again. So what I'll do is I'm going to impart a depressurization and see if we see a jump, okay? Nope, it's just decreasing. So it's interesting. So under pressure, the current definitely increases. So for what it's worth, I thought you might find that interesting. And I can check the voltage here too for you. Yeah, so the two cells in series. See where it stabilizes. That'd be interesting to see if that raises pressurization. I have not done that test yet. Let's tighten it back down and just check it for grins. Doesn't seem to be doing much anything. So voltage is not affected by pressure. So we're at like 50 psi or 60 psi now, and it's no different than when we depressurize it. Matter of fact, it decreases the voltage, seemingly. That's fascinating. Let's try that again. So here we have 2.744 volts at ambient. Now let's pump it up again, see what happens. That's fascinating, isn't it? Add pressure decreases the voltage. Don't know why that is. Again, that's at around 60 psi. 6.9245. Maybe it'll climb back up. It's interesting though that it decreases it. Maybe because of the temperature increasing inside the chamber, possibly. Okay, so there you have it. 2.7 volts. I'll decrease the pressure again. Definitely, you pressurize it and it decreases the voltage. Fascinating. So for what it's worth. Interesting stuff, still got a long way to go.